Welcome everyone to another evening with the Berlin Functional Programming Group. Tonight, I am very pleased to have Chris Penner, the optics expert, the profunctor optics expert, joining us. I don't know what biography I should offer for Chris. We almost met in Berlin when he lived here briefly, so we don't typically have actual native Berliners or even people living in Berlin do talks, but I think Chris qualifies. He spent 6 months here. He is the author of Optics by Example, where I suppose you can learn all about profunctors. Originally, the topic of this talk, although we have shifted gears a little bit, Chris is going to talk to us instead about deconstructing lambdas, whatever that means. I'm looking forward to hearing about it. I've been seeing all of his tweets leading up to the talk. So apparently he's very excited, which makes me very excited. I think we're gonna have a great talk, and I hope that everyone asks also some great questions. If you do have a question, Chris has built into the talk a few commercial breaks, so you can go ahead and note in chat. Either you can just say that you have a question and I will ask you to unmute when the time is right and you can ask your question yourself, or if you can't unmute because you don't have a microphone or something, you can just type your question directly into chat and I will read it for you. If you would like to support the meetup, that is to say supporting me and running this, this little pandemic gambit, you can buy one of these lovely t-shirts or support us on Patreon, and I will put some links into chat for you, and they will also be available on YouTube. This video is being recorded and you'll be able to rewatch it there. I always have to rewatch these videos because I have to spend enough time kind of coordinating that I can't always pay 100% attention. So I hear they're all really great, and I'm sure this one will be really great as well. Chris, thank you for taking the time to join us from Canada. I know it's the middle of the day for you there, and it's a Friday. I'm really excited to have you, and I'm going to hand it over to you now. And all yours.
All right, let me just share my screen here. Thanks so much for the awesome intro, and also thank you for sacrificing your Friday evening to be here with me. I know that's not your usual time, but it's just
I did have one beer before leaving work.
Perfect. All right, so you're ready to go.
I'm totally loosened up for you.
All right, cool. Well, let me just make sure all my tech is recording here. Looking good. Got too many monitors going on. You know how it is. And then we will get started. Okay. So I am going to be talking today about deconstructing lambdas, like Stephen said. This started off as kind of a profunctor talk, and as I got into it, I kind of just realized like, oh, actually, there are other more interesting things here, and I got sucked into this whole rabbit hole, and here we are. So we are about to embark on an awkward guide to programming without functions. Let's get going. Okay, so I'm Chris. I like doing handstands. I write Haskell. I wrote the book Optics by Example, as Stephen mentioned, which is just kind of an introductory guide to lenses and ISOs and prisms and all of that good stuff in Haskell. It takes you all the way from complete beginner to expert. And you can check that book out. I've got a little coupon code here at the bottom. So you can screenshot that or copy paste that or whatever, or just ask me for it on Twitter later. I've got a blog at chrispenner.ca if you want to check that out. And I'm on Twitter at ChrisLPenner. Cool. So as we get started here, I want you to just take a minute and think. So here's what we're going to, sorry, I'm getting ahead of myself. I got this overview for the talk here. We're going to talk about what functions are really, how I consider functions to be actually harmful in several ways. And then we're going to see how we can actually rebuild these functions from first principles, break them down into pieces. And then I'm going to have a little section where we talk about how we can actually represent functions as data. So that's where we're going. To start off with, what's the deal with functions? Have you ever actually sat down and thought about them? How do they work? Why are they special, right? Why are they so pervasive, right? They're foundational in modern programming languages, right? And for the last, I don't know how many, 30 years, 40 years, basically every single programming language I can think of has some variant of functions in there. even completely different paradigms, right? Functional programming versus object-oriented. We both still heavily depend on functions. So these are a pretty core concept. And one of the reasons, obviously, is they're incredibly adaptable things. They can model encapsulation, right? So you can kind of separate your chunks of code into different functions and spread them out across your app so that you can reason about them more easily. But you can also abstract different workflows, right? So you can pass functions parameters and you can customize their behavior. So it's actually a really useful tool for that as well. You can stack functions on top of each other to build your app, right? So this function calls this set of functions, and then those functions call these set of functions, and then it kind of abstracts over multiple layers to your app. It's a really handy thing to be able to do. But they're also composable kind of in a pipeline style. And we see this all the time in Haskell, right? We might have these kind of workflow engines, or maybe where you do this, and then you do this, and then you do this, and you can actually compose functions that way as well. So all of these things together, like it shows their power when we see that most modern programming languages actually model their entire program as one big function. So they're also modeled on lambda calculus, which is actually Turing complete. So when we choose functions as our abstraction, we know that we can actually compute anything that is computable, and that's a really nice property. Okay, so I've made a pretty strong case for functions here that I don't think anybody needed convincing on, right? They're clearly very useful. They come up all the time, but my opinion, functions also have a pretty nasty dark side that we don't really talk about, and we kind of just forget to think about it. So they have this assumption baked in, right? They assume that we plan to execute them. That kind of sounds silly. Like, what else would you do with a function other than apply it to its arguments, actually execute it, and have that behavior, take place? But there are a bunch of different things we can do. We can, for instance, analyze them. We would love to be able to do this. We would love to be able to maybe discover performance characteristics. Maybe we would like to figure out the big O notation of a function. We can do some semblance of this using compiler and linting tools, but it's not quite the same thing. And it's a little bit more abstract, and we can't do it at runtime. Why not? Like, functions are objects, we can pass them around. Why can't we inspect them? I would also love to be able to show functions. I'm sure everybody here has run into, cannot derive instance show for data type, whatever, because they've got a function hidden inside there, right? And we maybe just take it for granted that we can't show functions, but have you ever sat down to think like, why do I have that assumption? Why is this the case? Why is this restriction there? Some other things I'd love to be able to do is debug functions better. I'd love to be able to step through them iteratively, kind of piece by piece, maybe execute them one bit at a time. I'd also love to be able to transpile my functions, right? Just because I'm writing code in Haskell, I would love to be able to actually have this function be able to move it into a different language. Maybe I want to transpile it into JavaScript or Python or something like that. And that seems a little bit weird at first until you realize, well, we do this with data all the time, right? So I can write a data structure in Haskell and I can compile it down to JSON and then send it over to Python, and then it can deserialize it into its own data structure. So if we can send data between programming languages, why can we not send other things like functions? And that's kind of what I was just talking about there. I would love to be able to serialize my functions, maybe to send to a different language, maybe to send over the wire, maybe to save them to disk so that I can load a function later. And of course, there's like security concerns here. It's not really safe to run arbitrary functions, but I want to draw your attention to arbitrary. Well, a function is only arbitrary if we can analyze it, right? If we can analyze that function and break it down, then we can regain security because we understand how it works and what it's going to do. Okay, so functions, I think I've kind of clarified, are kind of weird in Haskell. They're like a primitive type. And it's one of the very few completely primitive types in Haskell that we can't really build ourselves, right? So we can't pattern match on it. We can pattern match on almost literally anything else, right? Like even Booleans in Haskell are like definable at the user level. It's just a user level concept, but functions are special. Why are they so special? So we've chosen as modern programmers to build our languages on top of this function abstraction, right? And did we actually choose the right thing? You know, we've been working with this for 30, 40 years. Has anyone actually revisited this and said, you know, is this actually the right abstraction for us to be using here? Okay, so if anyone has questions about that first chunk, I have just a second, a little break here. If anyone wants to jump in, I'm gonna see if I can pull up my Zoom window here. I'm not sure quite where it went.
I'm keeping an eye on the chat for you. I don't see any questions at the moment, but does anyone have a question? You can jump in now, type something into chat. Cool. I'm trying to stall a little bit.
For sure. Okay.
Not yet.
Not yet. Okay. Well, feel free to keep that in mind. I have several of these breaks as we go along. Okay, but we haven't gotten to the interesting stuff yet, so that's probably expected. Okay. Great. So let's continue. Okay, so functions are too powerful. So why are functions too powerful, and why is that actually a bad thing? Okay, so with functions, we have one large, super powerful type, and that actually provides less information than if we had several small, less powerful ones. So let me kind of motivate that claim here. So monads are very similar in this regard, and maybe something that you've thought about a little bit more. So we do have actually like a very similar comparison type here. We've got a primitive monad, right? We've got IO, which is kind of this, you know, opaque structure. We don't really know what's going on in IO. Maybe like we can case match on it, but we're just going to find a function inside, and there's nothing that we can really do. We can't analyze it. The only thing that we can do with an IO monad is really execute it. So you're seeing it's quite similar to functions in that regard. So if I were to show you a particular IO action, and I ask, you know, what does this thing do, right? I have this action, do the thing. What is it actually going to accomplish when I run it? Well, I mean, it could launch nukes. For all I know, it might just heat up my CPU. Maybe it just spins for some reason. Maybe it loads up a picture of a cute cat. I have no idea, right? This could do anything. It doesn't really tell us anything about what it could possibly do. So in order to understand kind of what's going on in one of these things, I need to break it down so that I can actually discover some more context about what it's doing. So we do this with monads all the time. We kind of have this MTL style, right? And we can actually break down this monolithic data structure into constraints which limit what you can do with it. So these constraints give you a set amount of power. So if we have a monad logger, then, well, inside this monad, we can obviously log things. Monad DB allows us to access the database. Monad state, well, maybe we have a user in scope that we can kind of edit or read or something like that, right? And by looking at this, I can see exactly what this monad has the capacity to do, and also a hint as to what it probably is doing. So we can see that actually this is strictly less powerful than IO, right? I probably can't read or write to disk using these constraints, but as a result, it has given us more insight into how it actually works. So we have this thing called the rule of least power. So for any given application, a programmer should use the least powerful tool, which can still accomplish that task, right? So if we follow this rule, we end up with knowing that the more powerful the tool, the less we can know about how it's used. Okay, so functions are similar in this regard. I've kind of made that analogy, where functions have too many behaviors that are all bundled together into one thing. And as a result, we lose the ability to introspect them, just like we do with IO, right? Kind of GHC just handles all of that and says hand waving like, oh, I'll execute that somehow, but it's too complicated for me to break down for you. So I'm just not going to let you do anything with this. So as a result, just like I can't tell what an IO monad is going to do, if you give me a function, I can't tell, maybe is that function going to loop on itself? Is it going to recurse? You know, does it ever actually terminate? I can't tell if a function is total. I can't tell if it's going to crash. I can't tell if it's just going to spin forever. I can't tell a function's execution complexity because I can't break it down. I can't reinterpret its behaviors in any sort of way. Maybe I want to compile it to JavaScript. Can't do that. All we can do is execute it, just like I/O. So what we need to do is we need to identify each of those kind of sub behaviors, like we did with the I/O monad, monad DB and monad state, and all of those sorts of individual behaviors that we need in order to do our job. And we want to abstract over them into independent behaviors, right? And then we can build constraints. And once we have those constraints, then we can kind of not only see what's going on, but we might actually be able to interpret them in different ways. So I got another little act break here. So feel free to chime in before we start breaking down these functions if you have any questions about what I've talked about.
I see two questions. Noon asks, hang on one second, just have to scroll up. Regarding serializing functions, do you think of source code as a serialized function?
In a sense, yes, but I would say it's a very unstructured serialized function, right? So you could, in theory, right, do macros and transformations on text. It's something that you can do, but nobody wants to do it, right? Because it's completely untyped, it's completely dynamic. You don't really, you kind of have to embed your compiler into it if you want to do that. So yes, you absolutely can consider it a serialization, but it's not a very practical one.
Okay, and I think there's a follow-up question from Gabriel. Ulrich, I see your question as well, but I think Gabriel's might be related to this topic. They ask, so is encapsulation a bad thing? Is encapsulation a bad thing?
I don't think so. No, I think it's actually incredibly useful. And I don't think encapsulation, maybe I misrepresented my point here. I don't think encapsulation is one of the bad things about functions. I think the problem is that functions can do so many things at once, right? And so maybe encapsulation is a really good thing, but we need to kind of limit the constraints on either when that's happening or what a given capsule of code is able to do.
Okay, Gabriel, if you want, you can unmute if you have a follow-up to that.
Yes, hi. I just wanted to ask, so actually you're meaning you want to have something like a single responsibility principle, right? So a function that does one thing and just one thing if possible. And if it's good for the user to notice what it does from the name or something like this, you don't care so much about what's inside the function, how it's done, right?
Okay, so I think I understand where the disconnect is coming in here. So I'm actually, for most of this talk, I'm not going to be actually talking about kind of organization of code in a given application, which is where kind of that sort of single responsibility principle comes up. I'm going to talk a little bit more abstractly about the concepts of functions themselves and not necessarily how you arrange functions in your app. I'm going to kind of zoom out a little bit and say, well, what happens if we reimagine the idea of a function itself? So I'm not going to really get into prescribing single responsibility principle or anything like that. I'm more interested in actually breaking down the functionality of how a function works. So I think probably the disconnect here came from the monad example, where oftentimes, that monad, right, you might embed constraints that require a single responsibility, and you can see when you break that. But I'm actually talking about the capacity for functions to do more specific things, which will absolutely be hopefully clarified in this chunk here of the next talk.
Thank you.
Okay, then Ulrich has a question.
Yep. Hey, also regarding the definition of a function. So I hear your function is basically what Haskell has as a function, not what a mathematical function would be like, just the concept of a mapping from domain to codomain.
Right. Yeah, so I think you're absolutely right. I'm talking more so about the more practical version of a function that is meant to execute code on your computer rather than the mathematical sense. And I should probably clarify that because I think there are a lot of disconnects, right? So a function in C, for instance, is very different from the mathematic definition of a function. And I think that mathematic functions are quite well defined and have very clear semantics and particulars. But of course, in practical real programming languages, we don't have that. So that's more the type of function I'm going to break down.
Okay, no more questions for now. Thank you.
All right, so let's see. So that was a really great question is, you know, what sort of behaviors and what sort of things are we going to be talking about? And this is going to have to do with the more practical, like, okay, if I have a function that I could execute, what could it possibly do? So we want to break it down into its component pieces and its component constraints. So you may be familiar with the arrow type class. It's in base in Haskell. Excuse me. And it is one kind of attempt to do this, to break down a function into different behaviors that, you know, a different sort of arrow might implement. Unfortunately, if we actually look at the arrow class, we can see, well, we have this arrow constraint, and well, first thing here is the ability to embed a function, a full power, full fat function into our arrow, which means if we can't analyze the function and it's embedded somewhere in our type, we're back to square one, right? Because we know we already can't break down that function and that function could do anything. We can no longer have any guarantees about this abstraction. So it's just kind of the same as if you have an IO monad in the base of your monad stack, sure, you might add additional capabilities on top of that, but at the end of the day, anything that can run in IO could conceivably run in that monad stack, and you don't have any guarantees about it. Okay, so let's try again. Let's start kind of from scratch here. So first things first, what are these behaviors that a function can actually do, and how can we kind of break those down into behaviors? So by defining classes for our behaviors, we can then choose any interpretation of that behavior which implements the type class. So just like monads. So let's look at some concrete behaviors here. So what I mentioned earlier is that functions can compose with each other, right? That's something that we can do with functions, but it's not limited to functions. So we'll see in a second here. So we do this in Haskell all the time. This is f composed with g, aka we will run f on our input, route that output into the input of g here, and we just kind of run one function and then run the next one on the output. So we can encompass this using the category class. So this is a standard class in base, and it has kind of two behaviors that you need to implement. One is you need an identity arrow. I'm going to try really hard not to say function for most of this talk, because we're not talking about functions. We're going to talk about the generalization over functions, in this case, categories. And so a category has an arrow, in this case called k, and it can go from any type to itself. And it is not supposed to actually perform any computation, make any changes, anything like that. That's just how it works. And of course, we can compose two arrows together. So if we have these two arrows and they have a type in common, so this arrow starts at X and goes to Y, this one starts at Y and goes to Z, we can actually line them up together and we get an arrow that goes from X to Z here. We're mostly going to be using actually this variant throughout the talk. So it's actually just flip compose, and it just composes from left to right, which can be a little bit more natural sometimes when we're writing code. So here's kind of what the diagram looks like, right? We have some type A, and we can route it into a B by going through this arrow F, again, not necessarily a function. We can run ID at any time, and it does nothing. It just kind of ends up where we already were. And we can, of course, keep going from B into C through G, right? And so this is the composition of F and G with a little identity in between. So with only this one class, we can already start to abstract over functions and do some interesting things. So I can define combinators that only use these constraints, right? So I'm going to use K here as my category. And rather than using a function from A to A, I'm going to use a category from A to A, okay? And I can define this combinator thrice, which takes some arrow and just runs it 3 times. Okay, so if it's a function, it's going to run that function 3 times, but maybe it's not a function, maybe it's something else. So we're going to see what some of those look like soon. So of course, it still does work with functions because functions are a category. So I can, for instance, run +1 3 times, and that gives us this add 3 function, which of course I can just apply to 10 and it'll add 1 3 times. Pretty standard. Okay, but we can introduce other categories. So just as functions in Haskell form a category, the idea of functions in JavaScript also form a category. Okay, and I can encode this JavaScript category into a type class in Haskell. We're going to see how that works. So the JavaScript category is exactly the same as kind of functions work in Haskell. We have JavaScript values, which are the objects of our category, and we have JavaScript functions, which form these arrows from one object to another. Okay. The identity function, of course, in JavaScript is just the identity function in JavaScript, and composition is still just composition of functions. So nothing too special there. So we need a data type now to encode this in Haskell. So I'm going to define a new type. It's just a type wrapper, and I'm going to call it a JavaScript func here. And it, of course, has to have two type variables if it's going to be a category, because it represents an arrow from one type into the other. But you'll notice actually these are phantom type parameters. Okay, so I'm not using them in my structure at all. I have this JavaScript function, and it just includes the textual representation of that JavaScript code, which seems a little funky, but we'll see how that works in just a second. And of course, it has this field function, accessor function here, which given a JavaScript arrow will render it into its textual equivalent. Okay. So those phantom types, although they're not actually used in the type, the data of the type, they do help keep things safe because it allows us to tag JavaScript text with type hints, right? So if our JavaScript text represents a function, we know what that function is going to take and return in terms of Haskell types, which of course we can easily map into JavaScript types in most cases. So let's actually implement our first class, our first behavior in the land of JavaScript in Haskell. Hopefully that's not too confusing. So we're going to write an instance of category for a JavaScript function here. And of course we have the ID arrow, which just goes from any JavaScript type to itself. So I can just write that as text. This is how you write the identity function in JavaScript. No problem. I just kind of embed it in there. And now this value will, the type system will tag it with X to X. So it knows that whatever you feed it is what you're going to get out. And we can, of course, write compose. Normally, when you write the class definition, you'd use dot. But again, following our theme, I'm going to use the triple arrow here. So this wouldn't actually compile in Haskell, but it's close enough. You can just flip the arguments around if you need to. So we can take a JavaScript function from X to Y and a JavaScript function from Y to Z, and we can create a new JavaScript function that has the appropriate type X to Z. So if we take this JavaScript function F on the left and the G on the right, then we can accept, we can define this new function text here. So I'm using text interpolation. So if you see this weird bracket in the I, that just allows us to interpolate text into text in Haskell. It's a quasi-coder. So this value is going to be a function which takes this new input. So this would be this X here in the resulting function. I'm going to just inline my definitions of F and G. This is kind of a dumb thing to do. It's going to result in, kind of large code, but for simplicity's sake, this is the simplest thing that could possibly work. So we have the first function we're going to run, which is F. We have the second function, which is going to run, which is G. I'm inlining those function definitions and assigning them to a variable. And then I just call those functions, right? So I call the first one on the input, and then I call the second one on the output of that. And this is how we can define composition in JavaScript. Cool. Okay, so now that we actually have this behavior encoded, we can treat JavaScript functions as a category in Haskell. So I can create just a random JavaScript function here. I'm going to say this is a function from a number to a number, and it multiplies by 10, and that's just pretty standard. But then I can actually use this exact same thrice combinator without adding any additional help. It knows that this is a category, so I must know how to be able to apply it 3 times, and we get a new JavaScript function that multiplies by 1,000 instead. So if I want to, I can take this new function that it has constructed for me, I can render it to JavaScript, right? And we get out this JavaScript function. So we can see there's this outer composition inlined here. So we take some input, we define the first function we want to run is times 10. The second function is another composition, okay? So that got inlined as well. And that composes first and second functions, which also are just multiplying by 10. We call those two functions on the input, and then we call those, the outer two functions on that input. And it turns out, if I copy paste that into Chrome and I just run it, it actually works. We just wrote our first JavaScript function in Haskell using Haskell combinators without any compiler hacking, and we did it in userland. So that is just only using category. What other behaviors can we use so that we can build more interesting combinators? Well, when we work in Haskell, we actually have a lot of assumptions about functions, and a lot of these assumptions will also apply to Python, JavaScript, C, all of these other languages. And particularly in Haskell, we have this kind of assumption that functions can just copy their arguments at will, use them multiple times, use them anywhere in the function body that they want, or they can just discard them, right? If I decide I don't want to use an argument, all I have to do is put an underscore and it just gets thrown away, right? So in Haskell, that's a reasonable assumption to make. However, other categories can't necessarily do this, and we might either need not be able to do it, or we need to actually specify how that behavior is going to work in this language. So a prime example that has been in the Haskell sphere lately is linear functions. So linear functions must use their argument exactly once, and that means that they can't just copy a binding or a reference or anything like that all over the place. They also need to explicitly discard things, right? So same in C. If we want to copy data, we need to like malloc new data, copy it over. Same in Rust. And we need to actually free that data when it's done, which means we need to be explicit about when we discard things. Otherwise, we're going to get memory leaks. We can also think of electrical circuitry as a category. So if we have kind of electrical components, those represent arrows, which can change one electrical signal into another. And we can, of course, compose those components by just kind of wiring the output of this component into the input of this one. And that forms a category, right? It's a category in the physical world, which is pretty cool. But we need to be explicit. Anytime we want to copy a signal, well, we need to actually go get a wire from our toolbox and route it into a new spot. So we can't just assume that that's something we can always do. And if we want to discard a signal, well, we probably actually have to route that into ground or do something with it. Like we might not just want to leave a wire sitting out on our desk, right? Okay, so how can we actually encode those particular behaviors that are just kind of assumptions in Haskell and given to us for free by functions and encode them as a well-defined type class? So we can define this copy arrow, and this says, well, in your category, you just need to tell me using your categorical abstraction and data type and arrow or whatever, how do I take one thing and turn it into two, okay? How can I take a thing and throw it away, right? Like basically discard all data about this type and just get this unit type back, right? So maybe this is free if you're writing in C. Maybe this is routing into ground if you're doing an electrical circuit. And from that, we can kind of derive these other two combinators. So we have the idea that if you give me two things, well, I know how to consume one of them. So here I'm just going to discard the one on the right and take the left, or I can do, of course, vice versa and take the second element and discard the first. So that's how we can encode these things. So of course I can do that in JavaScript. You'll see throughout this talk, I'm going to represent JavaScript tuples as just an array of two elements in JavaScript. That's pretty common. That's how TypeScript does it as well. So I'm going to copy this element into two. To consume, well, JavaScript does have a garbage collector, so I can just throw it away and return null. Don't have to worry about special behavior there. And of course, first and second, I can do kind of the Haskell-y thing and just discard some elements there because the garbage collector will pick up on it. So nothing too complicated in JavaScript, but we can encode that behavior explicitly. There's a bunch of other plumbing that we're going to need that, again, is just kind of we assume that it exists. But the idea even that functions can route their arguments into either multiple internal functions or, internal functions that exist at different stages of execution. So let's take a look at a real example here. What's all going on? This is an extremely simple function, just is palindrome. It takes a string and checks whether that string is equal to itself in reverse. That's how we check if something is a palindrome. Excuse me. But there's actually more going on here than you might think. So one question I would have, how can we actually do this if we don't have the ability to apply or execute a function, right? How can we rearrange this, right? Like this implicitly assumes we're going to execute reverse and then pipe that as one argument, and then we have this string which is getting copied over here, and we're piping that into the other argument, and then we have to execute equals, right? How can we encode this without the notion of applying functions? Well, we need a little bit more plumbing. So I'm going to rewrite this function kind of in this form. So this is kind of a more composition-based format. So I'm going to define explicit lambdas here, and we're going to separate it into stages. So first, I can kind of do this explicit copy here, where I take one string argument and duplicate it. Then I can have a next stage where I take those copies. I want to apply the reverse function to one side, but I want to send the original string onto the next stage without editing it, so that we can then use it in this last step, where we have the reverse string and the string itself, and we can check whether those two are equal. So here I'm doing explicit argument routing. This argument that comes in at the beginning, I've explicitly routed it all the way to this last step. And that's something that Haskell gives us for free, but we need to encode it. So how can we encode that? I have this idea of a strong category here. It's also kind of like a monoidal product category if you're interested in Googling that, but strong is the name that, for instance, Komet uses in his profunctors library, which has a lot of these cool classes. That's based on the profunctor hierarchy rather than the category hierarchy, but it turns out they're almost interchangeable. You just have to change the superclass. So what can we do here? So we have these two combinators, first and second. And what they do is they say, if you give me an arrow that does something, I don't know what it does, but it goes from an A to a B, I can take an additional argument. I can return a new arrow to you that has an additional argument and just routes it to the end. And says, I'm not going to edit this. I'm not going to mess with it. I just need it at the end so I can thread it into maybe the next function. This allows us to do this. So it says, given an arrow, I will run it on the first half of a tuple or the second half of a tuple, but I'll also allow you to pass some additional context. So what does this diagram look like? We kind of need to see it. If we have some f, which is our arrow from A to B, when we run first on it, we get this thing. So it takes a tuple. You can see it's routing this A through F, but other just goes around. Okay. So it's really kind of a boring idea, but it's something that we need to explicitly define. So now that we have a little bit more power, we can start to define these combinators. Right, so here I'm defining this star, star, star combinator. You might actually know it from the arrow type class. We can re-encode it using category and strong. Category is a superclass to strong, so I don't technically need it here. That's just for being explicit. And this combinator, there's a lot of types on screen. Don't worry about it. Basically, what it does is it just composes first and then second. So we take two inputs. I'm going to call them L and R. And we'll run F on the left-hand side, and then we'll compose it with second, which will run G on the right-hand side. And we can simplify this down semantically into something like this. So given two inputs, I will run one function on the left and one function on the right. And that gives us a lot more useful power. We also have this other one, which is called fan out, and it takes one input and forks it out to two different arrows. So that looks kind of like this. We do an explicit copy of our argument, and then we route one copy to each side. So there's a lot going on. I'm going really fast here because we have a lot of stuff to get to, but you can see how this is taking kind of implicit assumed behavior for how functions work in Haskell and making them explicit. So of course, JavaScript functions are also strong categories, so we can implement this, right? So all we have to do is we take our tuple arguments here, and we can unpack them. And of course, I have this function, this JavaScript function, this category that I want to run only on the left-hand side. So I'm going to unpack it here and call it on first. Just going to inline it. And then I'm going to call it on the left-hand side and then repackage my results into a tuple. And you can see I've explicitly threaded this R all the way to the result, and it's not being edited at all, which follows our the behavior we need. Okay,
Chris, do you have a
let's
break?
Do some questions here before we move on to the next section. That's
okay,
great.
okay. Sorry to interrupt.
No, I was actually just going to ask.
Perfect. Okay. I mean, I actually have a question myself, just a naive, like, sanity check question. Since we're talking about categories, just to confirm for myself, you're defining the category as an identity, and then composition, right?
That's
So basically defining it purely by the arrows themselves. So the object in the category is defined by the identity function. And then you're defining how you would compose these objects together.
Yeah, so that's one way that the categorical definition of categories is kind of weird from a Haskell perspective, because when we talk about manipulating things, the things that we manipulate are actually typically the arrows, right?
Mm-hmm.
Whereas in a normal category, like, you wouldn't necessarily think of it that way. So I'm kind of blending the mathematic intuition with the intuition that you would probably have if you worked with categories in Haskell, but I believe you're right in your assumption there.
Okay. Just checking on that. I mean, I think it's perfectly legitimate to only care about the arrows, actually. It might not be like obvious for everyone.
Yeah. I'm
so by the way,
category theory expert, so I'm gonna, flub some of the specifics of it, but I hope that the intuition comes through, and obviously, hopefully the code clarifies any confusion, right? Because it's unambiguous. Yeah.
Yeah, and I wanted to say, I think what you're doing, I love this kind of thing. This is great for intuition, like building things up from scratch in this way in order to understand how they work. Ulrich has another question.
No, thanks. That was solved. Thanks.
Okay, and let me see. Reed has a question. If Reed would like to unmute.
Yeah, for sure. So a minor point here. I think your strong should actually follow from Cartesian. Normally you encode like the sort of mapping into pairs thing as the universal property of the products. So I think those two should be merged, perhaps.
Sweet. Yeah, good to see you, Reed. Glad you can make it. Yeah, I will absolutely take your word for it on that. That sounds reasonable. So basically, I think what Reed was explaining is that I wouldn't actually need a separate class for strong. I could actually just embed that into the Cartesian sort of definition, and presumably everything that could implement Cartesian could also implement strong, and so they don't need to be separated, which would actually, speed things up, clean things up a little bit.
Yep, that's it. And thanks for putting this on. This is awesome.
Yeah, it's so good to see you, Reed.
Yeah, I definitely agree about the awesome part for sure. Alex Ionescu has a question. Alex, would you like to unmute? Okay, maybe Alex can't unmute. Alex's question is, what if some objects in your category can't be copied?
Yeah, so that's actually a really interesting question, because it gets a little bit complicated, right? Because I'm kind of the Cartesian class that I defined needs to work over any possible A. So what you could do in that case, and what some other people who have kind of encoded this in Haskell have done, have included a type family with their category definition. So for your Cartesian category, you would actually have a type family or a type associated type, which includes a constraint. So the idea would effectively be, if you need that sort of thing, you would include a copyable constraint. And then in the definition for your copy, you would actually just require that constraint over A before you can copy it. So I left that out for simplicity, but that is absolutely a thing that you do need to worry about in certain cases. You can actually look into a lot of the linear Haskell stuff. There was a really, really great paper that just came out this month that actually goes into modeling linear functions using categories. I believe it's symmetric monoidal categories. So I think if you Google linear Haskell symmetric monoidal category, that paper should come up. Came out this month, I think, from Twig. And there's some cool ways to encode that in that paper.
Okay, thanks. I think that's it for questions for now.
Awesome. Let's build something. Let's get moving. So, okay. So I have this admittedly quite simple function, right? We're starting from basics here. And I want to rewrite this function so that it represents just the behaviors of what I'm doing here, so that I can actually run it in either Haskell or JavaScript using the exact same thing. And I don't have to rewrite it every single time, right? Okay. So we're gonna go back and we're gonna do this transformation again, but now we know a little bit more, right? I know about this first combination. So what I can do is I can start translating this kind of line by line and converting into a more general form. So first thing first, we have to assume that we don't have a function. Okay, so this isn't gonna compile, we haven't converted the rest yet, but I wanna say I don't have a function from string to bool, I have some category from string to bool, particularly some arrow from string to bool, okay? Sorry, I gotta stop saying some category from string to bool, it's an arrow from string to bool in a category K. So next, what we can do is we can see, okay, well, first thing we're doing is we're duplicating this value. So I can do that with copy, and then I just need to change this to a Cartesian constraint. Okay, so the next stage, I have exactly this pattern where I want to run some other category, right? I want to route 1/2 of my argument to this arrow reverse, but I don't want to affect the other one so that I can copy that argument all the way through the next stage. I can do that with first. So if I run reverse over only the first, the left half of that tuple, then in the final step, I'll have reverse and the string itself. And I can have these constraints here. And as Reed pointed out, actually, I could collapse these down, which is nice. Then I need to check whether the reverse of the string is equal to this string. Now, the keen among you might have noticed I still have reverse and equals in this definition. And of course, those are both functions, right? So we're not quite done yet. We need to talk about primitives, okay? So when we're getting down to brass tacks and we're talking about actual programs rather than, kind of staying in the nice theoretical level, we need to actually do things, right? So in all applications, there's gonna be some custom behavior that is unique to that application or that use case that we will not be able to probably encode using completely general classes, or maybe we just don't want to because it's going to be way too much work. So in this particular case, I'm going to define two primitives that we effectively just require this behavior from any category we are going to interpret into because we don't want to or we can't build it up from these general classes. Okay, so one I'm going to say is, well, rather than implement, reversing and like knowing about what your concept of strings is in your category and how to break those down and rearrange them, that's a lot of work. Whatever category I'm going to run this on has to implement reverse string. And whatever category I'm going to run this in needs to implement some notion of equality, which can take two arguments and turn them into a Boolean. Cool. So these primitives, any operation, again, that we've decided we just don't want to break down. And you can also do this for other reasons. Maybe it's for performance reasons. If we built it up out of those small combinators, it would generate something that's much less performant than defining a single simple definition. Or maybe we're just annoyed and we don't want to do all that work. So here I can make a class which represents those primitives. Okay, so we're basically defining our own category constraints, which we can of course do. So we have reverse string and we have equals, and we can implement that. So for functions, super easy. Well, reversing a string is just the reverse function. And our equals we can encode as uncurry of the equals function, which makes it take a tuple. Okay. So we've got an instance of our primitives for JavaScript functions as well, right? So here's a way to reverse a string in JavaScript that I, of course, just copy pasted from Stack Overflow, but it works. And we've got an equals function where we unpack the tuple, and I'm just going to use JavaScript triple equals, right? So here you can clearly see like triple equals is a primitive in JavaScript. So it makes sense that it's a primitive in our category here too. Okay, we have finally reached the goal, and this is a proper type checking encoding of this is palindrome. I don't want to say function, behavior is palindrome definition that works on any category which implements these constraints, which means, of course, we don't use any functions inside here. Well, so I also want to clarify, I am, of course, using functions to combine our combinators because I'm working in Haskell. And so, but the result is these functions are going to create an arrow which can be interpreted. So keep in mind that the functions I'm using to construct the thing and the thing itself are different. And so long as we don't have functions in the thing we're constructing, we're all good. Okay. So what can I do with this? Well, at the top here, this is our type, is palindrome. I can check the type of that and use a type application to say which category I want to use. So if I say I want to use a function, then GHC happily says, well, if you have is palindrome for a function, it's literally just a function from string to bool. And it's, it's going to work that way. And inference in GHC is actually strong enough that we don't need the annotation, because application in GHC implies that the type on the left is a function. And so we can just run this same thing that we constructed, even though it's generic over categories. We can just run it as a function and it works. It'll tell us whether something's a palindrome. I think that's pretty cool. So I can also say, what is the type of is palindrome if it was in JavaScript? And it'll tell me, well, it's a JavaScript function from string to bool. And of course, I can render that and then print it out. So this is the exact same is palindrome definition, but it's interpreted into a different category, and it'll use those different classes. So you can see here, the indentation is incorrect because I didn't bother adding a pretty printer. But don't worry, because JavaScript doesn't care about indentation either. So you can see our definitions are inlined here. Here's our reverse string, and here's our equals, and it's built up this weird thing. You're not going to probably pass code review with this, but you know what? JavaScript doesn't care. It works. We can embed it into Chrome, and we can run it, and it does the right thing. So that's pretty sweet. Do we have any questions about kind of how we have been compiling things into other languages, and or about primitives or those sorts of things?
Yes, we do have some questions. A lot of questions tonight. This is great. Ulrich has another question. He's very excited.
Yeah, maybe that's always the sign I don't really get it. So I'm, as a non-computer science major, trying to interpret what I've heard so far, and I get the picture of actually a virtual machine that has some basic instructions, which are your primitives, and that somehow gives me the picture that we're back in programming in assembly, but for that virtual machine, whatever it is. Is that the right way to picture what we're doing here?
Yeah, I think so. So I think we can imagine what I'm doing here as very similar to what a compiler does, right? So a compiler takes one representation of a behavior and turns it into a different one. This is exactly the same thing, except that our definition of that behavior is based on some mathematic sort of structures. And we have the additional benefit that we are not assuming that they're going to be executed, which means we can do some really interesting things. We're going to see some more examples in a little bit. But for instance, I talked about circuits, right? So circuits are a physical thing that obviously a compiler cannot build a circuit for you, but we can, using these mathematic definitions, spit out, for instance, a circuit schematic that you could build in the real world. So it's a little bit more abstract than using a compiler. And it gives us a really nice, clean, well-structured, lawful representation for this, which we can base on 100 years of mathematics rather than, whichever JavaScript VM someone wrote last week, right? So it allows us to draw on a little bit more of a structured background.
Yeah, but so your primitives could be the instructions of, say, the Java virtual machine, and you get out Java bytecode, and then that's still, of course, not executable as such, but you could do AST transformations on it or whatever.
Absolutely, yeah. So if you wanted to define reverse string and equals as either Java bytecode or literal just Java syntax, and then implement, Cartesian and strong in Java, and you only have to do that once, and then now we can interpret any possible combination of those combinators into Java from Haskell. Cool. Any other questions?
Yes, Noon has a question. Noon, can you unmute?
I can. Can you hear me?
Yes.
Great. Here's my question. Am I missing? I'm just a little bit confused. I thought maybe at the start I was kind of promised like that everything would be visible. The implementation would be visible, but the way I'm understanding it is it's just kind of moved to this category instance. Is that right, or am I a bit confused?
Okay, so when you say visible, I'm gonna assume here, correct me if I'm wrong, that you mean like as a value or as a tree or something that we can manipulate. Is that kind of what you mean?
Yeah, something, because you kind of didn't
Right.
like source code early on, so I'm kind of thinking I was
Sure.
going to get
We're gonna
something
get there.
else.
That's coming up. Yeah, so I'll defer that question until after we hit the functions as data section.
Okay, Noon says thanks. Georgie has a comment. I'm not sure if there's a question there. Georgie, did you want to make a comment or ask a question?
Oh, no, that was just referring to the previous question about visibility.
Okay, cool. Then, let me see. Bernd has a question.
Yes, I'm thinking of, is it just real JavaScript and Haskell code, or is it also mixed with pseudocode with all the brackets and backslash and add character?
Yep, so I mean, everything I've shown you compiles and runs, it's real code. And maybe I am actually doing a disservice to this idea by compiling it into a different programming language, because I think it actually causes us to think of this as just a compiler. And it is more general, right? Because we don't have to output code at the end of this. I'll hint a little bit in the future. We can actually output diagrams of our code. We can output circuit diagrams. We could, basically compile any sort of categorical structure. And it turns out actually a lot of those exist out of the idea of programming. I'm not sure if that actually addresses your question, but if you wanted to write an interpreter for this that just dumps it into pseudocode, you could absolutely do that. Or even a mathematic proof language, you could probably do that same.
Do you show also at the end some running code, for, not just slides, but also something to give a hand on?
Okay, so by that, do you mean the implementation for these things? Because like I've been showing literally all of the code that we've been using on screen so far. Is there something else you're looking, or like a GitHub repo or something like that?
Like for example, the last talk was also very theoretic, but at the end I've shown some examples, the workflow, and then it gets much more clear to at least to me for what's going on.
Well, so I do have lots more examples coming up here. So hopefully those will clarify. If it's unclear at the end, maybe we can circle back to that. Yeah.
Just quickly, so you are defining some arrows from the category of, what would you call it? The category of Haskell functions, or the category of Haskell types, to the category of JavaScript functions?
Right.
Okay, so these are just functors.
Yes.
Okay.
Yep, that's pretty much exactly like, well, I mean, so what we're actually doing is effectively creating a free category where we're actually not defining which category we are in. We are only defining the properties that are required of that category, right?
Yeah.
And then we can actually pick which interpretation of those ideas we want. But if you wanted to, yes, you could consider it a functor from like free categories into specific categories.
Okay, I saw the Cartesian constraint and I thought maybe there was like a clue about what's coming up. A few more questions have rolled in, I think. Ulrich wants to know, what if your primitives are not Turing complete?
If your primitives aren't Turing complete, that's actually typically a good thing, because that just allows you to know even more about which sort of thing you're interpreting as, right? So there's no requirement for your primitives to be Turing complete. You can choose the depth of your primitives based on your particular application. So if you want to limit the power of your users, for instance, you want to do a DSL, or you only want to allow them to encode certain things, pick a small set of primitives. If you want to allow arbitrary computation, you can literally have a primitive that lifts a function into this categorical representation if you want, but then you lose any analysis over that particular primitive, right? Because we can't, in general, introspect our primitives, but if you know what type your primitive is, you can of course do that. So primitives allow you to pick as little or as much power as you want. Does It's at your discretion.
Okay, I think we can move on.
All right, let's roll. We got lots of stuff. I might, well, yeah, we'll get through it. Okay, so next sort of behavior that we maybe take for granted. Hopefully I've proven that there's at least a few things about functions that you haven't thought about, and that is branching. So I'm going to define a new little function for us to look at. This is a Haskell function which goes from int to int, and it runs one step of the Collatz conjecture. If you're not familiar, all that is it's a conjecture that says if you take any number, well, if that number is even, then you divide it by 2. If it's odd, then you multiply it by 3 and add 1. This is just one step of it. And the idea is if you do that over and over and over again, presumably, it's never been proven, all numbers will end up as 1 eventually. We'll reach there. Okay, so what's going on here? The most important part of this is that we have 2 bits of code here, divide by 2 and 3 times n plus 1, and we will not ever run both. There's branching. We have to select one branch of code to run. Okay, and this is something we haven't seen yet. So we can't take branching for granted. This ability to do if then else, certain categories support it, other ones don't. And it's actually useful to know like whether a chunk of code branches. So going back to kind of the interpreters example, if we do decide to interpret this into bytecode for some VM, if it's a JIT compiled VM, or it does optimistic execution, it's really, really handy to know whether any code in that chunk is going to branch, because if it doesn't, you can really ramp up that optimistic execution because you know exactly what's coming up. And branching isn't always trivial depending on which category you're in. So in certain cases, like circuit diagrams, right, you might actually, in order to branch between 2 signals, you might need to implement a multiplexer or something like that. So it's important that we define this. But in order to talk about branching, we first need to define coproducts, right? So we need to be able to work with this idea of this thing or the other thing. So in Haskell, we represent coproducts typically as either, right? So if we want to say we have maybe an A or a B, we would represent it as either AB. And we can introduce this co-Cartesian category. Okay, so this is the dual of Cartesian, but not by flipping the arrows, it's by flipping products into coproducts, okay? So these are all kind of flipped versions of the Cartesian category. Actually, I think it does flip the arrows too, if I look at it. Yeah, that's right. Okay. So we add the ability to inject a value into one of these coproducts. So this arrow just takes A into either A or B, can do the other side. And we have this ability to unify. So we can take either an A or another A. And of course, since we know that they're the same type, we can just kind of collapse them down into one path and we can join that split again. We can join that branch. This is a combinator. It's not actually really part of co-Cartesian, but it turns out it's just useful to have on hand. And all this does is it's an arrow that witnesses the isomorphism or the equality between a Boolean and an A and an either AA. So this just takes that Boolean and decides how to tag this A. If it's false, it will return left. And if it's true, it will return right. So again, this isn't necessarily a property of co-Cartesian, but it's something that turns out it comes in handy when we actually use it. Okay, I'm not gonna spend a ton of time on this. I won't show that Haskell implementations are all trivial. I will point out that we're going to represent our coproducts in JavaScript. There's many different representations. I'm just gonna say we have an object with a tag on it, and that tag is gonna be left or right, depending, and then they have a value. Okay, so those are just the implementations there. Now that we have that, we're ready to make some choices. Okay, so branching is one thing, the ability to represent multiple branches, but we do need to actually decide which branch we want to go down, and we want to be able to run code on one branch and not the other. So I'm going to define another category here, choice. And I think probably Reed is chiming in right now to say likely choice is expressed by co-Cartesian, but I have it split up for the purposes of this talk. You can see that in Comet's profunctors library as well. And this does a very similar thing to strong, where it runs an arrow over one half of a product, but in this case, it's on a coproduct. So we say we can take as input either an A or some other thing. And if you give us the A, we'll run this arrow. But if you give us something else, we won't. So this is much easier to see with a diagram. So we can see here, if we get the A, we'll go through F to get to B. But if we get something else, we will skip it. Okay, and this gives us this ability to branch and execute some code, but not others. I say code, again, it's abstract. And of course, we can define these combinators the same way. So because we have composition, we can run something on the left, something else on the right, and collapse that down into something that looks like that. So that's this combinator. I'm going pretty quick here. You don't really need to worry about these types. It just does this. It allows you to branch one side through F or the other side through G. So this lets us choose which code we want to compute based on our coproduct. And of course, I can make an instance for this in JavaScript. So I'm not going to belabor this too much. Basically, we inline the function we want to run on one side. Then we check our input. And if it's the left, we run that JavaScript function. And if it's not, then we'll continue down here and we'll just return it because we know it's got to be the right-hand side. So that input gets threaded through if it's not the left. Okay. That was a lot. Don't worry if that code is very confusing. I'm going to go through this pretty quick so we can get to the more interesting stuff afterwards. But if you want to see how this works, let's go through. So we need to first detect whether the input is even or odd. And that allows us to choose to either divide by 2 or multiply by 3 and add 1. So these two lines are unique, mutually exclusive code paths, and we're only going to do one or the other. Before we can actually do that, you'll notice we have a lot of numbers in here. We have not talked about how to handle numbers in our language. We could, of course, encode that as primitive, but turns out numbers are just kind of useful things, so we can define a class for that. And we require the ability to embed, because we're building up this category in Haskell, we say we use a function to allow you to embed a Haskell integer into that category. So there has to be some way for you to construct an arrow in your category, which operates as, again, the only thing we can work with is arrows. So this is going to be the constant arrow, and it takes anything and just returns an integer. Okay. We have all these other nifty things, so we can require an arrow that negates its argument or adds 2 arguments, multiplies, divides, takes modulo of 2 arguments, right? Those are pretty standard. So of course we can implement that in Haskell functions pretty trivially. It's just uncurry of everything, and we use the const function for num. And for JavaScript functions, it's similarly trivial. For the number one, I just kind of lift that number into JavaScript. And if it seems weird that we're not just embedding it as a number, it's because the only thing that we have to work with is our arrows. And that has to do with kind of the weird way that categories are encoded in Haskell, where you work with arrows as your things that you can manipulate. But regardless, all of this should be pretty straightforward, just a bunch of operators. Okay, so we've defined how our numbers work. I'm going to define this additional helper. And the implementation of that is not super important. It just shows that we can continue to build combinators if we find that we're doing something a lot and work at a higher level. So here's our function that checks whether a number is even. Okay, so of course, if you're looking at this, this is a lot of code to just check whether something is even. We're going to come back and talk about syntax later. But all this really does is it takes an integer, it runs mod2 on it, which I define below, and then it checks whether that number is equal to the number 0. So this strong combinator just allows us to express kind of function application, but it's not really. It's expressed using these constraints. Again, this is going really fast. I apologize for that. We'll get to some more interesting stuff after this. So here's our mod2, and basically it says, given an argument, I want to copy it, turn one side into the number 2, and then run modulo over the original argument and this altered version. So this takes its input modulo 2. And so this should spit out whether a number is even. And of course, because function implements all those classes, we can literally just run it. It's a really nice way to test that we built it correctly. Here's the next little combinator we're going to need. And this takes a predicate arrow and turns it into something which chooses either the left branch or the right branch for a given value. Okay, and I just use this tag combinator to do that. So I run the predicate and then I pick whether to tag that input as either left or right. And of course, once we have all of those things together, we can actually build this function. So again, don't worry too much about the code. I have a lot of code on screen. We're just going to cruise past that. So effectively what we're doing is we're going to match on this predicate arrow, whether our value is even. Then we're going to use this combinator, which is going to run on odds on the left or on evens if it's a right. And then we're going to have either int, and we're going to unify those together to our output. And those are the definitions. You can see we're just multiplying by 3 and adding 1, or dividing by 2. Great. So I can run this whole step, and you can see that it works. So 3 times 3 plus 1 is 10. 4 divided by 2 is 2. So odds do one thing, evens do another. Now, here comes the fun part. We can render all of this to JavaScript. So all we've done in JavaScript, right, is said basically what are numbers and how do those work? How do we represent choice? How do we copy and manipulate values? Those are the only things we've defined. We've written all of our collabs code in Haskell using this sort of combinator library. And we get this. So again, probably not going to be passing any code review anytime soon. This is an absolute mess. Keep in mind, I'm doing the dumbest possible thing. I'm literally inlining every single function definition of every combinator that we've defined. So you could absolutely clean this up. But the important thing is that it does still work, right? So I can copy paste that into Chrome and it does the right thing. So that's pretty cool. This is definitely alpha level software. I just kind of, you know, each of these things I wrote up in less than a day. It could use a little work. Okay, that was a lot. Now we're going to see some other cool things. So we've talked a lot about JavaScript functions and Haskell functions and all of that stuff. What about some other cool categories? So I can interpret all of these categories, classes that I've shown you into actual diagrams which represent the behaviors that they're encoding. Okay, so I can define a new type which represents a diagram. Okay, I'm going to be a little bit hand wavy here just for time. And I can represent a diagram as a state monad over some graph type. I'm using the algebraic graphs library here. And some, this is going to always have a value in scope, which represents the inputs to a given diagram and the outputs of a given diagram, right? And so in a graph representation, we can kind of keep track of like where we're linking into and where we're linking out from using this representation, and we can keep all of our nodes in this graph. And so it turns out I can actually render the diagram for a collapse step. I won't give you too much of the implementation here because it's kind of boring and it's mostly mechanical. If you want to see the code later, maybe I can show you that. And this is what we can get out. So now we're talking, right? So this is the actual diagram that I generated from that code on the previous slide. And we can see we start off with some input. We can track this whole behavior. We copy it, which forks it into 2 different sides, right? So on the one side, we're going to copy it again, branch it out, turn one side into 0, and mod the other side by 2, check whether that's equal to 0, use that Boolean to tag the original value, pass that in, and this will now be either left or right. So we make a choice. We can either go to the right, which means it was even. So we copy it into a 2 and divide that input by 2. Or we multiply by 3 and add 1, unify those into the output. So we can visualize our code now, right? So this is effectively the equivalent of showing a function in a way that, you know, it is long form. Again, I wrote this, the code to do this diagram in like less than a day. So it could absolutely be cleaned up. We could represent our inputs and outputs better. We could probably tag our arrows with types, those sorts of things. Most of the diagrams you've actually seen in the talk were generated from this code. I just basically punched in the code, ran it through, and you know, put whatever I got into the talk. So I think that's pretty cool. It gives us a high-level view of any function. And you could actually use this, for instance, if you write, let's say, your web server routing logic using a category abstraction, you could view at a high level, you know, which requests are going to which handlers and why, which predicates are running on them, to pick which routes you want to run, those sorts of things. And you can use that to either debug your function or just kind of detect whenever things change. Okay, let's stop here for a question or two. And then I'm going to go through really quick a few other behaviors before we get to the really interesting representing functions as data stuff.
Cool, we do have a few questions. Gabriella has a question. I need to ask it. Is this whole approach similar to free monads, where you encode your monad's basic operations and then later can manipulate it as data or interpret it, except we are now doing it for arbitrary functions / arrows and in a more general way?
That is exactly what we are doing. And the next section is about free functions. Little spoiler.
Okay, and then Evgeny has a question. Evgeny, would you like to unmute? Maybe,
hi.
Maybe not. Okay, hi, go ahead.
Yeah. So looking at this presentation, particularly the diagrams reminded me of compiling to categories paper by Connell Eller. How different is it basically the same thing, or there are some differences?
So it's very, very similar. And the idea is Connell's paper, as best as I can understand it, he compiles general Haskell code down into a closed Cartesian category, which is a very specific set of these constraints. And the constraints that he's chosen actually have a slightly different hierarchy, such that he can encode all of the things that we're doing, but he has a little bit, that approach is less amenable to analyzing things at runtime and in user level code. So as far as I understand it, it's a compiler plugin. Definitely go watch his talks, read his papers on this. He's done this effectively in production and is rendering like circuits from Haskell code, which I think is super cool. This is breaking this down and viewing it from a slightly different perspective. But if you understand what's going on here, it's almost the same thing that Connell is doing.
Thanks. Yeah.
And we have one more from Gabriel, if you'd like to unmute Gabriel.
Yes, I wanted to ask, is it possible to draw the graph or the diagram and then produce the code from it?
Interesting. Well, so the idea would be, I think you could. What you would need to do is write kind of a reverse interpreter. You would need to, given a graph data structure, you would need to break it down and interpret that data structure back into these generic constraints. Or, as we see in the next section, if you can render your graph into this free function data that I'm going to present, then of course from that free structure, you can turn it into anything, right? So just with free monads, it's the same. If you have a particular monad and you are able to interpret that into a free monad, then you can reinterpret that free monad into any other monad that implements it. So it would be a little bit trickier, but you totally could.
Yeah, thanks. And one more question, maybe I missed it. Is there also a representation of loops that can be done this way?
Yes, indeed there is. We're about to get there.
Okay, thanks.
Okay, that's it for now. It's funny how when you start dealing with things at the categorical level, everything starts looking like everything else.
Mm-hmm. Totally. And I love to see those patterns kind of pop up. It helps you just kind of view code in a new way, just like Haskell, monads make you see things, everything different, and suddenly you start seeing them everywhere. I think.
Yeah, exactly. I really hope you do, I don't know, some kind of maybe mini book out of this talk. It would be great.
That would be very cool. All right. So lightning round. I really want to get to the functions as data part, and there's a lot of ground to cover here because it turns out, as we've learned, functions actually do a lot of different things, right? That we need to kind of break down in order to do all of this stuff. So this talk did end up being like quite a bit longer than I was hoping. But we have a couple more behaviors. I don't want to spend too much time on them. Just trust this works. So let's go through some of those behaviors. So one is that functions can swap arguments around. And we can encode that as a symmetric category, which is the idea that given a product or a co-product, So tuple or either, we can just swap the order of those arguments. It's really trivial. Or we can, for instance, reassociate those products or coproducts. Okay, so this is really trivial in Haskell. Keep in mind that the reason we need to define this, if you think about swapping these, if you're writing a PCB, right, like you're doing a PCB diagram, if you want to swap this signal and rearrange it so it's on the other side of this signal, like you probably need to punch a hole through to the other side of the PCB and then go across and then come back. There are categories where this stuff is not as trivial as it is in Haskell. So that's why we need to encode it. Okay, functions can recurse. So this goes into kind of that looping concept that we were talking about. The way that we do folds or loops or that sort of thing in functional programming languages is typically through recursive functions. So if we want to do arbitrary looping or recursion or anything like that, or get any semblance of Turing completeness, we're going to need to be able to define looping. Here is the class that does that. It looks a little funny, but it does work. So the idea here, this is called co-choice in commits profunctors. Probably a better name would be some sort of, recursion category. And sorry, this should say class here. And this has this unleft, it's kind of a poorly named, at least in this interpretation of this class combinator. And what this does is it's kind of the opposite of choice, as the name implies. But the behavior of it is that if you give me an arrow which can accept either an initial value A or some continuing value C and returns either a final value B or some continuing value C, the category needs to know how to convert that arrow into one which goes from input into output. So the category itself knows how to wire up this output continuation into, this output continuation back into the input. So what's going to happen here, we're going to first run the arrow with an A. If we get a C, we run the arrow again on that C. If we get another C, we run the arrow again on that C. We keep looping through this arrow until eventually it returns a B, and then we exit. Okay, so that's a little bit confusing, but this is what it kind of looks like. So I apologize. I'm definitely at this point mixing metaphors. I have functions as objects and types as objects, and I should probably go back to the drawing board on this diagram. But the idea is if we have some arrow F that has this loopy structure, unleft will unwrap it into something that takes an input, loops around in here for a little while, and eventually returns an output. Okay, and if it loops forever, it won't ever return that output, but it's still modeled the same way. Okay, so that's how we encode loops, but there's another type of loopy thing that we haven't talked about yet, which is CoStrong, and CoStrong encodes fixed points. Okay, so fixed points are kind of a type of lazy recursion, but it's something that we actually, it turns out, comes in handy in certain categories. This is one that, fewer categories actually implement this, but this is how we do it. So rather than a product that's loopy, we have, a coproduct that's loopy, we have a product that's loopy. So we have a tuple that already accepts the result as a continuation state and then returns a value and that continuation state. So this looks very similar to the fix function in Haskell. And our category needs to be able to collapse that using laziness or some other measure, running that fix function on it to get just a regular arrow as the output. Okay, we're not going to spend too much time on that. If you're interested, feel free to dig in, check out the CoStrong and CoChoice pieces of the profunctors library. They have lots of cool implementations. Now we can model all of these different things: composition, branching, swapping, copying, routing arguments around, recursion, fixed points. And that mostly encodes the majority of functions that we might want to write. I think maybe all of them. I have not yet done a proof that shows that every function can be encoded as those classes, but I haven't yet found a function that can't be. With the exception of the closed class, but we're not going to get to that today. Okay, can we also encode classes for reader, writer, state, continuations, IO, all of these useful things that we want to do? I'm kind of breaking into monad land, but it turns out actually every single one of these monad classes has a category equivalent, right? So you can have a category that can access context. You can have a category which can write data as output. We have a category that can keep kind of a mutable state around. And you can actually encode continuations as a category. And of course, if you know anything about how I/O is implemented, in base, I/O is just the state monad. And if we can encode state, well, of course, we can literally encode I/O as a category, which I think is pretty cool. Check out the Cleasley category in the arrows kind of area of Haskell if you're interested. Okay, we have arrived at functions as data. So this is going to address free functions and some cool new interpretations. Before we get to that, were there any more questions?
I don't see any questions in chat now. Maybe since you've asked, a few may come in. We have decided in chat that you do need to do a book or some kind of like small pocket guide though.
Awesome. I think that would be really fun. I think that would be fun. Maybe that'll be my next one. Cool. Okay, functions as data. So I mentioned in passing as a response to a question earlier, the idea of free functions. So if you haven't heard of kind of free types, I definitely don't have time to explain all of it, but it's the idea that a free type for either a free monad or a free monoid or a free function is a data structure which can encode those behaviors and those constraints without giving them any additional semantic interpretation. It's the minimal type which can encode all of those things and nothing more, okay? So here is an example of a data type which encodes a function freely, right? I'm not doing all of the classes here just because it wouldn't fit on the slide, but you can imagine I have a constructor for every single function that I've defined so far. So what is this? Well, this is a GADT. It's a generalized abstract data type. And I take these two arguments here. We'll come back to the P in a second. And, well, I can encode the identity arrow just as a data type, right? And this is just a token. There's no data included in here because you add your interpretation of what ID should be when you turn this data structure into your specific category, okay? We have compose, which takes two other representations of functions, and it just stores them because we're going to need to interpret them later. But for now, we'll just encode them as a tree, as data. Copy, right? Consume. All of these things are just tokens that can be interpreted later. Okay. And this works for this version. Just implements category, Cartesian, and strong. But you can do this for all of the other classes I've explained. So here's the actual implementation of these classes, right? ID, flip, compose. All of these are literally by definition just the constructor. So if you're curious how you would construct the other types, take the type signature and just turn it into a data type. Okay, these are all, what about primitives, right? So primitives have multiple different, right? Like you might define your own sets of primitives. And how do we encode those freely? Well, we can pretty easily encode them freely by accepting this type parameter here on our free function. And this type parameter can represent any type of primitive that you want. And we just have a layer of primitives in our structure. So we say at any point that you want, you can just lift some value that represents your primitive into our free function, and everything else will just kind of work around that. And you'll have to interpret it later, but we can defer it until then. Okay, so here's an example of that. If I want to define the primitives we talked about earlier, I make a new data type, right? And this is a GADT. And I can actually provide types here too, right? So on the free function, I actually forgot to mention, all of these are typed, right? And that's why we're using an abstract data type here, is these are guaranteed to be composed in the correct configuration because, for instance, copy, it outputs something of this type, even though it's just a phantom type parameter, okay? So Haskell will guarantee that our structure is sound and correct by construction. Okay, back to this. So when I define this primitive type, I can say this is a primitive, this is basically the free primitive that goes from string to string. And equal, I can say, well, I can take any two things that are equal and turn them into a Boolean, okay? Then I can write that instance of my primitives for this free type that lifts it into a free function by just calling lift. All right, so I'm going really quick here, but this shows how we can encode any thing that we've seen so far as a data structure. So we come back to is palindrome, which uses these constraints. I've shown how all of these constraints are implemented by our free function, which means we can encode this function, this behavior, this process as data. And we can do that pretty simply. First, I'm going to derive show for all of my free types here. And it turns out Haskell can actually do this for you. We need a little bit of quantified constraints magic. We just say for any primitive that can be shown, we can show a free function by just showing the constructors. That's not the important part. Then I can say, is palindrome use the free function with this set of primitives and show it to me. And it dumps this out. So this is obviously not the most readable representation of this function you could possibly imagine. The reason for that is because I'm lazy and I didn't write like an ASCII diagram renderer, but I could presumably take that diagram code that I wrote and have it output ASCII diagrams that actually show the routing of arguments through your function if you wanted to. And then you could show this function. So since our function is now data, we can also serialize it, right? Because data can be serialized. How would we do that? Well, let's say we want to dump it into JSON because we want to send our function over the wire or save it to disk. We can write a to.json instance. So here's to.json for our primitives, right? So we just take each primitive and I'm just going to dump it into a string. There are safer things you could do. This is for the sake of example. And for any free function, so long as our primitives can be dumped into JSON, then we can dump the entire free function. And we do that again, just by either constructing strings, which represent the operation, or constructing objects which contain the operation and its arguments, right, as JSON. So that's no problem. Again, you can probably do more things to avoid conflicting names and stuff like that, but we're not going to get into that. Okay. So I can call to.json on is palindrome, and we get this, right? And it's a pretty reasonable representation. Oh, sorry. I think I actually changed, I changed definitions here. I switched it to an array-based format and forgot to update the code. Sorry about that. But this is equivalent. So you can see we're composing copy with the composition of running first on our lifted reverse string primitive, and then routing that into our lifted equal primitive. So, I mean, all of this is just encoded as JSON. Deserializing the functions into Haskell is unfortunately a little bit trickier because we need to if we want it to be well typed, we need to actually reinterpret type information from the JSON value into a Haskell type, which is really, really hard and would be considerably easier in a language with dependent types, right? Where we can actually infer types from values. So that is one kind of blocker. It's a little bit tricky. You can get around it by assuming that your JSON is correct by construction and interpreting and handling any type errors as they come up. I'm not going to get super deep into that. It's a thing you can do. It'll be slightly less type safe, and that's unfortunate. But lucky for us, other languages aren't so strict, right? So you can write interpreters in Java or in JavaScript or in Python, which take a JSON object and interpret it into classes or objects in their language, which implement those functions, and then you can run it. And this means that we can actually safely send and accept functions over the wire because it is a completely introspectable data structure. That's really important. So we can actually validate the structure, make sure it only contains primitives we know about, and we can choose our set of primitives that we want to support. So we can say, okay, well, we're not going to add a primitive that deletes our entire hard drive. So if we don't have that primitive, this function can't do that, right? Because it's not an arbitrary function. It's a very specific function that we have declared. So you can define your own DSL using primitives, but then the user can wire up those primitives however they want using the full power of functions. So we can also check for divergence, right? Or totality by inspecting the structure. Because if we don't have the ability to loop, the function must be total unless one of our primitives breaks that rule, but that's on you, right? You just need to choose which constraints you want on your primitives. If none of your primitives loop and you don't have strong or co-strong in the data structure, which is super easy to check, that function will terminate. It won't loop, it won't diverge. Pretty cool. You can also interpret it iteratively, right? You can peel off this data structure one node at a time and interpret it step by step. So you don't have to worry about, oh, maybe they wrote a function that's way too long. You can do time sharing. You can run it as a fiber that can be paused, or as a coroutine and do it bit by bit. You can do time sharing, all of this stuff, because we can actually analyze our structure. This has a lot of cool applications in things like, Beam or Hadoop, where this is kind of infrastructure as a service that lives in some companies just kind of have this running on code. But if I want to write a transformation that's going to run on these sort of systems, I need to write it in Java, and I need to go over to their service and do it, because it needs to be interpreted into their sort of internal language. They have a few built-in interpreters for certain common programming languages, but there isn't a structured way to do this. Most of them are ad hoc. Most of them use operator overloading and something equivalently hacky. This gives us a common data structure based on math that can be used in any language. And I can write these Beam functions in Haskell, given that they define a set of primitives which work on Beam, and send them over the wire safely. I think that's really sweet. Okay, we can also optimize any of these operations. So because this is a data structure, you can think of it kind of like an AST. So if you have kind of this tree, you can introspect it, analyze it, and you can optimize it. So you can say, oh, well, okay, here I see we're doing a branch, and then another branch, and then another branch. We've got like 5 if statements in a row. Why am I going to branch all those times? I have like this conditional construct in my language. Maybe we're in Lisp or something. I can actually do a case statement or a branch based on this, which is going to be much more optimized, much faster. So you can look through those things, or you can find dead code paths and you can just remove them. It's pretty cool. Okay, so summarizing everything we've looked at, basically we've learned that functions are a conglomeration of many different behaviors that all just kind of got lumped into one thing called functions, and that it gives us too much power, so that we can't actually limit our options, and we can't tell what those functions are doing because it's just too much at once and we can't break it down. We learned that we can do a lot more with code than just execute it, right? But that our current representation of these functions is preventing us from doing that. There are lots of other interesting categories that aren't just programs. And here are some examples, right? So some ideas. Verilog is a category. Connell built something that I think renders down to something similar to that, schematics. You could compile your Haskell functions into Minecraft Redstone if you really wanted to. There's nothing stopping you. You can write optimized GPU code, right? You can turn your function into something that runs on a sat solver or runs probabilistic Bayesian analysis. So you can tell kind of what are the chances of each of these branches being taken. You can run things non-deterministically by substituting primitives with functions that return multiple values, right? And you can run each branch. You can encode linear logic in this, like linear arrows using this approach. You can do FRP, state machines. You can detect places in your functions that can be parallelized and do that automatically. There's lots of cool things that I just haven't dug into and don't have the time to do in this presentation. So we learned that we can encode these functions as data, and that gives us a lot of power because then we can analyze, optimize, or serialize it. And we also learned that the syntax here could use a little bit of work. I'm very optimistic on this, actually. So even though those functions that we saw were hideous and unreadable, it turns out that actually the kind of adaptation of normal Haskell code into that style is pretty mechanical. Definitely something that we could look at having a compiler do for us, because we already do that a lot, right? So I would say the same for monads, right? If you took away do notation, everybody would think that monad syntax was horrible, right? Like all of those nested closures, all of that stuff. It's pretty rough. This is the same, right? We can absolutely either adapt arrow notation, proc notation, write our own thing to make this much, much more palatable. So don't get held up on how ugly the syntax is. That's a solvable problem. I would also be very interested to see if any new programming languages would adopt categories as their primitive for the language. So what if you built an entire language around this idea that, you know, your base unit isn't the function, it's more granular? What would that look like? So these principles are all sound, even though there's like a few messy bits in here. It's based on, you know, how many hundreds of years of math. So that's kind of cool in the sense that it's not just an ad hoc approach. You know, we have papers we can read. I had a slide here. I think we already mostly mentioned how this is very similar to Connell Elliott's compiling to categories. I would absolutely recommend you check out his talks and his paper. His paper is actually quite readable. And just Google Connell Elliott's compiling to categories if you want to dig a little deeper. He takes a slightly different approach, which is it optimizes for different things, I should say. The approach I went for kind of allows you to reason about things at a slightly higher semantic level because it has more behavior split off. And that can be useful in certain cases like diagramming, where you kind of want to see things at a slightly higher level. But Connell has done some amazing things in compiling his code into actual working like circuit boards and stuff. So I hope you learned something. In closing, I'm Chris, still Chris. I have a blog at chrispenner.ca. I write about a lot of stuff kind of like this whenever I have the time. I'm on GitHub at Chris Penner, and I'm on Twitter. Just go follow me there, Chris L. Penner. If you're interested in kind of my teaching style or anything I talked about, I happen to think my book turned out pretty well, so you can go check that out if you want to either read that or send it to a friend and learn about how optics work or lenses work and how they can really up your Haskell game in a really practical way. It's a very down to earth and you know, applicable in your everyday life. And there's a coupon code here for something like 50% off or something like that. So feel free to pick that up or send it to a friend. But yeah, with that, I'll say thanks to Stephen for planning and running and organizing all this. Thanks to all of you for showing up and joining me on this fun little voyage and, you know, giving me a reason to learn all of this. And I'm sure we probably have a few more questions in chat to take a look at.
Thank you. Yeah, that was fantastic. Everybody buy Chris's book, and thanks for the discount code. I'm just curious, you're suggesting that we might want to give up some of the power that we get from functions by going to like a more general level, essentially, in the same way that you might want polymorphism. Like something that's more general rather than more specific. Like you give up power on purpose for some reason. So
when I say give up power, I more so mean break down that power into discrete and understandable units, right? So the idea wouldn't be necessarily that we lose anything, but that we know exactly how much power we're using at any given time. And we know exactly how each of those behaviors is going to be interpreted so that we can implement it in a different, you know, category, right? So you can then choose which level of power you need, which it turns out is really helpful because certain things that we can do in Haskell, you might not be able to do in a circuit schematic, which means if you want to interpret into a circuit schematic, you might actually need to limit the power that you have, which functions don't allow you to do. It's all or nothing, right? So this allows you to, if you want full power of functions, you can add all of the constraints, it's no problem, or you can just use functions. But if you want to get more granular, you absolutely can.
Right. By generalizing to arrows, we can cross into different categories, like go into different universes and maintain the same conceptual structure.
Sure.
Okay. Yeah, I mean, my mind is definitely a little bit blown. This is very cool. It's nice to have my mind blown periodically. Alex has a question, probably referring to something from a little bit in the past. Alex Ionescu, once again.
See if I can figure out how to pull up chat here.
I'm not sure what Alex is asking about. The question is, could we also do something similar for type constructors, but at the kind level?
Something similar. So, I mean, if you want to work with different categories at the type level or at the kind level, I mean, presumably so. I would absolutely not want to write that code in Haskell. You could probably do something like that a lot easier in something like Idris, right? And define, manipulate, because like, right, we have type level functions. So presumably that's just a category, right? It's a category of functions over types. And you could absolutely do all of this stuff at the type level. I just wouldn't do it in Haskell. You could probably do it in Idris though. Definitely give it a try.
Ulrich has a few more questions. Go ahead, Ulrich.
Yeah, actually, just one specific question. Wondering the categories you picked, do they follow from any criterion, or are they, I mean, how do you come up with exactly the ones you've been using? Is there another set that would do the same thing? Are they total in a certain sense? Are they minimal? Yeah.
Right. So as far as like kind of academic background on that, I don't think I've ever actually seen this, like I've never seen this exact set of categories broken down, maybe for better or worse. I do know there are other ways to do this sort of thing. For instance, Connell's compiling the categories. The way that he does it is by picking closed Cartesian categories, right? And we didn't talk about closed today, but it is strictly more powerful than some of the things that we've talked about, right? So if you add closed, it gives you things, I think like things like recursion built into that, but in such a way that you can't tell how exactly it's being used at such a granular level. I would also say, like, a lot of this stuff, there's a lot of research done on comparing the simply typed lambda calculus to categories, and specifically how you can represent it using a closed Cartesian category. I haven't seen the more practical approach here where I take like non-theoretic functions, actually like executable functions, and break them down. And I pulled these categories from a little bit of research, a little bit of other papers, some from the profunctors library because I saw that they encoded something useful, and just kind of thought a lot about functions and what they can do, and made sure that I had a class which represented every piece of it. So it's entirely possible I missed some. It's entirely possible there is a nicer way to do it, but I don't think I've ever seen it actually broken down this way, and it seemed reasonable and interesting. So I guess I'm going to follow Cunningham's law here and put it out into the world and see if anybody corrects me. It's a good way to learn.
Right, thanks.
KK asks, is this work also related to your original planned talk on profunctors?
Interesting. Yes. So I started, I probably will come back and do that talk at some point. I started this by looking at those classes that were from the profunctors library. So choice and strong and co-choice and co-strong, and I realized that they were really useful for some reason, and I didn't know exactly why, and they were useful for modeling these other categories. However, when you go down the profunctors path, you actually run into a very similar problem to arrow, which is the idea that every profunctor must be able to embed a function inside it, because the profunctor class has die-map, which allows you to lift functions into a profunctor, right? It allows you to map functions over a profunctor. And that was a sticking point for a long time. So my original talk, I just kind of ignored it and went around it and tried to get everything to work. Eventually, I realized why it wasn't working, and that categories were the more correct representation. And that's kind of why I pivoted. But there is a lot of fruitful ground in representing programs using profunctors and optics-like structures that I would absolutely like to get deeper into. And it's a very, very powerful encoding that you can do almost anything with. But this is the one that I ended up getting sucked into, and I think there's more to look into. Of course, we're never done.
Okay, Alex is also interested in your slides, actually. Which tool did you use to make them, and are they available online?
For sure. I haven't uploaded the slides yet. If you follow me on Twitter, I'll make them available probably in Dropbox or something. I don't know, Stephen, if you have a place to put things, but
I don't have a place to put them, but I can put a link on the YouTube video.
Sure. Yeah. Okay. So I'll get them to Stephen, and he'll put them on the YouTube video, and I'll post them on Twitter, let's say shortly after this. As far as the actual code to run all of this stuff, it's currently very, very messy because it's gone through a bunch of different iterations. I would like to make that available so people can play with it. What I'll probably say there is I'll at some point, well, I don't want to commit to too much, but I'll probably write a blog post at some point or post to Reddit with a GitHub repo that has some of these ideas like the diagramming and the JavaScript function code. I apologize for not having that ready for today, but just keep an eye on me on my Twitter and on Reddit, and it'll come up eventually.
Yeah, I think the interest is actually in the tool that you use to make the slides themselves, I think.
Yeah, for sure. So I really love this tool, actually. I'll go to bat for them. It's called DECset.
It's DECset. I thought it might be DECset. Yeah, I use this for everything.
It's wonderful. I really like it. Go support them. They built some cool stuff. So the way that this actually works, I write all of my slides in Markdown. So I'll actually pull them up here if you're curious. And it's all just written out.
Markdown to slide, right? Sold.
Yep. Yeah, it's great. So I love it because I can just dump my code in here. I can do search and replace. If I want to edit a slide, I just search for it. It all works perfectly in version control. Highly recommend it. It's a lot of fun. You just pick kind of your themes. You can stylize things to a certain degree. I do wish, if anyone from DECset is listening, I really wish it would like center code like this, but you know, there's a few quibbles, but it mostly works very well. And you can of course export to PDF.
There's some hacks that you might be able to do. I'm not sure about centering code specifically. I messed around with it quite a lot in my own presentations.
Yeah, there are some features.
Yeah, great tool, definitely worth paying for. Couldn't agree more. Back to the topic. Jan Zieger has a question. Jan, can you unmute? Maybe not. I can ask the question.
I have to click, sorry.
Oh, there you are. Okay.
Sorry. So I was just wondering, like, I mean, in Haskell, you already get some security by having just the type signature, right? You get the inputs and you can create some outputs from that, but you also get stuff from the environment. So you could conceivably, you could just restrict functions by restricting access to things outside, like, yeah, via their environment. So like if you don't have IO functions, okay, that doesn't apply to Haskell, but if you don't have like looping functions or something, then you can't really loop. So that would allow you to like program, let's say, normally and still get the benefits, but then you wouldn't get all the other, like the abstract interpretation benefits, I'd say.
Yeah, that's right. Yeah,
that
and I didn't show it in this talk because I mean we're already at 2 hours, so
yeah.
Didn't have time. But there are also interesting ways for the free function constructors. There's a trick where you can limit your free function constructors to a subset of the classes that you want to support. So if you wanted to, you could say, I'm going to construct a free function, but it does not support looping. And the GADTs will actually enforce that you cannot have the looping constructor. And then you can actually unpack it in a case statement, and GHC will be like, nope, you don't need this one because it's impossible. That's quite neat.
Cool. Thanks for, and I apologize for this not really being a question.
Can we do 2 more and then perhaps call it a night? Or call it an afternoon where you are. Noon has another question. Go ahead, Noon.
Yeah, maybe my question was a little bit similar to that last one, but I was just wondering if you'd talk a bit about, let's say you have your JavaScript interpreter and then you want to compile it down to something else that doesn't have a copy ability. What does that look like?
Well, so I guess you have a couple options. One is that you can restrict the code that you can compile down into it to any sort of arrangement that does not have this Cartesian constraint, right? So if the code and the combinators that you've written don't require the Cartesian constraint, then you're all good, right? The type level ensures that you won't need to handle copy. If you do have copy in your code, you're using the Cartesian constraint and you want to turn it into something that can't copy it, I mean, you're out of luck unless you can implement, like, it doesn't have to semantically copy, right? It just has to match that type signature in a sensible way where sensible is defined by your interpretation. So if we think back to the circuit category, if you want to copy a signal, like, you can't just copy a signal, but semantically, if you fork that signal and you make sure all of your voltages and your currents stay the same, maybe you use a component to do that, it's fine in the context of your domain, right? So you can kind of pick and choose how you want to implement copy. It's completely up to you. You just need to give some definition.
Okay, and I know that other people are asking questions. Maybe Chris can have a look at the chat after we finish, but I think we'll do one more for the recording. Maddie has a question. Maddie, can you unmute?
Yeah, so yeah, I guess this might be a rabbit hole, but I was curious about if there are, you can talk about laws that these different categories have to satisfy, such as like composing with identity gives the same thing as the arrow. And is there a way to talk about arrows being the same without going into rabbit holes of infinity groupoids and some nonsense like that?
So I will not actually dig into all the categories. Well, first off, I apologize. I have committed a sin. I gave a Haskell talk and presented classes without laws. That's my bad. But they all, of course, have laws because they're all based on mathematics. So I would just point you with the mathematic literature. Just Google all of these different category names. NCAT has lots of good stuff. All of this stuff has laws associated with it. There's 100 years of math to read about. So I would say just go dig into that. There's people smarter than me who've written all of that stuff down, and there's algebras over categories. There's lots of fun stuff to dig into, and that's why I think this is really fruitful ground to build this on top of category theories, because you get all of that stuff. Yeah. So, but I'm not going to go into all of the specific laws here.
Okay, thank you, Chris. There are a few more questions in the chat, so maybe we'll end the recording, and if you want to stick around and answer a few, people can unmute and you can have a chat, or if you have to go, we can also end it here. This was a really fantastic talk. Is this the first time that you've presented these ideas and this material?
Yeah, actually, I do conference-driven development. So I ideated, discovered, and implemented this over just the past 4 weeks. So it's a little bit rushed, but I really enjoy, kind of having reasons to learn all this stuff. I'm definitely looking forward to having a little break. It's been on my mind a little too much for the past couple of weeks. But.
Conference-driven development. I haven't heard that before, but yeah, I like the concept.
Topic-driven development, if you prefer TDD.
I mean, I would be very interested to see what you do with it next. I wish there was some way for the meetup to sponsor your work, because I think this would be really useful for people who started to learn about functional programming to even develop their intuition further. Like, these kinds of projects are just great. So I'll say once again, thank you for joining us. It's really nice to get to meet you finally. And I hope we can do this again in person someday.
Great. Yeah, thanks so much for hosting. Really appreciate it. Great to meet you too. And thanks to everyone who showed up.